Bernardi from Italy, La Sapienza, University of Rome. I made this project, sailing system for Cubesat Deorbiting, with my teammate Giorgio Vignali. We build a system that deorbit a Cubesat of 3 units. We exploit a free and used volume offered by the standard solar panel. The core idea is that we use this volume, that is the volume between the structure of the Cubesat and the internal wall of the P-pod. We have some constraints, like the maximum thickness of 7 mm, because the constraint of the Cubesat says that the external device mustn't touch the internal wall of the P-pod. This SSCD is composed of 4 wings. Each of them increases the cross-section on 0.36 meters per meter. Totally the system deploys a sail of 144 meters square, like I show in this picture. Each wing is independent one from the other. Here we have the orbital parameter says by the DDC guidelines, the teacher says before. We put this orbital parameter in the DAS program, a program made by the NASA, the debris assessment system, and calculate the orbital decay for this orbit and our mass area ratio. And we see that our system re-entry in 2 years. This is the mechanics. We have 2 levels. On the first level we have 2 external bars that rotate of 90 degrees with respect to the axis perpendicular to the structural plate, as highlighted in red. And the second level we have 4 longer internal bars that rotate of 180 degrees. The main component is the structural plate. This is the internal face. It's made by aluminium with this dimension. This is the face that is in front of the Cubesat structure. Between this face and the Cubesat structure there is the this mechanics here, and the sail. On the other face we have 2 pockets where we can store the solar cell, here and here. The other components are the rods. We have 2 main rods, shorter rods in this dimension, and 4 longer rods made in aluminium. We have also the spring made in harmonic steel with maximum thickness of 2 mm and maximum rotation angle of 180 degrees. We have a torsional spring of we have a torque of 10 Nm, and the sail is made of miter with a maximum thickness of 190 micrometer and a tensile strength of 190 megapascal. The mechanical connection is made by a clip that create a connection between the spring and the rods. Here are shown the deployment of the sail. This is the external face. The sail is here between the structure and the plate. On the first time the plate rotates on 90 degrees. Then the first 2 shorter rods rotate on 90 degrees respect to the perpendicular to the axis. to the plate, and then deploy the longer rods. In this slide I didn't show the sail because in this way it's easier to see the mechanic how it works. And we made a first prototype. Here we have the structural plate is thicker than the project because our drill cannot create something thicker. No. This is stored, our configuration is stored, and then this is the configuration deployed.
So it's a time for question.
Your system looks mechanically quite complex. Did you ever deploy this mechanics with the sail to see if the concept will work reliably? Or did you only deploy the booms, the aluminium parts that you show there in that you showed in this slide? Have you also done the same thing with the sail attached?
No, I didn't put the sail because there is some problem on the connection here. We didn't have the miner in our lab. And also because this is our first prototype, is just to see if the mechanic works. In fact, we have some issue to
What is the mass of your proposed system? The total mass
is 200 grams, 300 grams, but is quite heavier than the final product because the heavier part is this, and this must be 2.5 millimeter, but in our first prototype it is 5 millimeters. 5 millimeter are much heavier.
And you need 4 of those for a satellite. You need 4 of those.
Yes.
So if it's 150 grams times 4, it will be about 600 grams for a full satellite, for a 3-unit satellite.
You attach solar cells on a panel side. Solar cell. Yes. And how does a harness goes to the body?
Sorry?
How does a cable from the solar cells to goes to the body?
Allora, here there are 2 pockets, so you can put the solar cell and then create a hole here and here, and put a wire that connects the solar cell with the structure.
Did you design the routing of the solar cell cables? I think that affects your motions of the panels, because
But when we deploy our system, the satellite is dead. It's at the end of life, so we had no problem with the solar cell.
at the end of the life, the cable may be very stiff, because the cables have been already exposed to space environment, and then the cable may not be soft anymore. It may be very stiff, so it may be very difficult to deploy. Did you think about that?
The cable are in the internal wall.
Yeah, cable at the hinge. This,
You say can
it may be very
stop
stiff.
the motion.
Yeah. Yes, it may be very stiff.
We can put the cable in the here where is the joint, like in the joint in the computer, in the netbook. So they didn't create problem like this.
Yes, at the beginning, yes, but I'm not sure at the end of life.
Because you say may is
Because the cable material may changes
yes.
because of exposure to environment. That's one comment.
You could use
You-
a more powerful spring.
Okay.
How do you start operation?
How we start operation?
Operation of the deorbiting.
How?
How?
We use thermal cutter that
The onboard computer.
the onboard.
Is it with a command?
Allora, the onboard computer says send a signal to a thermal cutter.
So what if the computer is dead?
We can put this program in the onboard computer of the main on the bus of the light. It's a simple switch. I send a signal and
And it wouldn't know when to deploy. No?
using the antenna we can send not us to the satellite the signal when to deploy, or we can put a clock when the time is
Another thing,
reached.
you say you get the power from the battery.
Yes.
And what if the battery is completely depleted? It doesn't provide energy. What if the battery doesn't provide any energy? Because
You can use
if
the
the
solar
mission
panel.
time is long,
We can use the solar panel. We need a very low power to turn the system. It's almost mechanical.
and have you also considered the lifetime of the springs? For short
Yes.
missions is not a problem, but say if you have 10-year mission, would it function?
Yes, we say on the the technical report that they say the constructors says that it will work for 10, 5, 15 years
But in space environment,
in space environment.
it's for spaceships.
Yes.
So I have two questions. The first one is, do you have any idea to fold the membrane in such a very small body?
The mylar.
Yes.
The mylar is over here, and I think we first fold this part, the lateral part, and then the connection between the mylar and the longer rod is only here, so we can store the mechanics and then over the mechanics fold the mylar, like the bed on the bed.
So have you ever tried some folding method?
Measure of
So have you ever tried some with some prototype or something?
no, I
Okay.
didn't already try to fold the mylar.
My another question is about the latch mechanism. You use the torsion spring.
Yes.
So in a store configuration, the spring should not be deployed. So I think some latch mechanism or something is necessary. Am I right?
Sorry, can you
Latching with
Latching.
You latch your spring so that the overflow is spontaneous. How do you latch your spring?
Ah, ok, allora. Here we have on the side of the structure two L-bar that block the motion. So when it turns, because the L bar are here, are attached to the structure, and they didn't rotate. So when it rotates, the rods are free and can motion and can move.
Right.
How do you open that? Is there
We
latch?
have another
Is there
torsion spring here.
latch? But what keeps it down?
Thermal cutter is like an electric lamp. When the current passes through, it blocks and it's like a wire.
But you said that if the battery fails, you can use the solar cells. Will the solar cells give you enough current to thermally cut that wire? On this question, you said that if the battery failed, you can use the solar cells to supply the current for the thermal cutter.
Yes.
But will the cells be able to supply high enough current
They require very low power.
to cut thermally?
Yes.
Normally it's a couple of amps.
Half an amp
We
or 1 amp?
need only a little thermal cutter because we have the torsional springs provide a low torque, so we can use a very little thermal
So
cutter.
then you must make sure that the sun, the thermal energy from the sun will not deploy your thermal cutter.
Yes.
Well, I have a question about impact on the bus system, the Cubesat bus system. I understand that your system covers the 4 surfaces of the Cubesat, right?
Yes.
And in that condition, I think the flexibility of thermal design as a satellite is reduced, much reduced. What do you think of this aspect?
I think that this system impact on the thermal design like a normal solar panel with manual torque, because the thickness is the same and the materials we use only aluminium.
Like, I think the thermal radiation is prevented by your system. So if your system covers 4 surfaces of Cubesat, then the Cubesat cannot radiate their heat through the 4 surfaces. So I think this impact is large for the spacecraft's thermal design.
Thank you. I think we don't have enough time. So let's thank again our speaker.